In this video, we will look into this concept, that is finding out the connected components of a graph. So, and we will be solving this particular problem, which which is based on this concept, and also there are a couple of more concepts involved in this problem which are really good and which are basic but really good. We need to understand those in order to solve hard problems of graph, because they will be useful in couple of places in DP and other things. So first thing, let's try to analyze what is connected components of a graph. Let's say there is a graph which has these nodes like 4 and 5 and 0, 2, 3, and the graph is like this. So if we understand, like if we look at it, there are three connected components of a graph, right? Connected in the sense there is path from any vertex to any vertex in that subgraph. This is a total graph, and in every subgraph there is a path from any vertex to any vertex in that subgraph, and there is no path outside of this subgraph. So there will be three connected components in this graph. Like the definition is not so good, like, but you can look at it and you will be able to understand. So next thing, how will we find this? So it's very easy. So what we will do, we'll use normal DFS. What we will do, for we will loop over every node, like we will 0, 1, 2, and we will apply DFS on every node. And what it will do, we will use a common visited array. So by the time DFS finishes this, so on node 1 will be marked. Next, when we do this thing, when we do apply DFS on node 0, 2 and 3 will be marked visited, and the DFS will traverse this. Next thing what we will do, we will apply DFS on 1. What it will do, it will mark 1 as visited. Next what we will do, we'll come to 2, but 2 is already marked visited. It was part of a connected component or subgraph of 0. So 2 will not be we will not be applying DFS on 2, and the same with 3. Next we will apply DFS on 4. It will mark 5 as visited, so we won't be applying DFS on 5. So there will be like three connected components, right, in this subgraph, in this graph. So next thing, what we have to actually solve, this is very basic concept, we are just revising this. Next thing, we have to find out, as this problem suggests, says, we have to find out the number of complete connected components. Connected components of a graph. So what does complete mean? So what it means is, the a connected component, it is a connected component, but in which there is an edge between every pair of vertices. That is like this. See, if you see, this is a pair of vertices, there is an edge. This is a pair of vertices, there is an edge. And same with 2, and same with 0. But here, there is no edge between these two pair of vertices, but there are edges between other two, but this pair has no edge. So it won't be counted as a connected component, a complete connected component, although it is a connected component, but it is not counted as a complete connected component. So how we will solve this? So the very first thing is how we can solve. Let's say we have to find out whether a connected component or a subgraph is complete or not, right? The definition says that it is like every pair has a edge, right? Every pair means two nodes. Every two nodes has edge. So what is this? Like we have to count, if we have to count how many pairs will be there, or how we can, if we know number of nodes in that subgraph or connected component. Let's say for this, uh, let's say this, consider let this connected component. So if I know like the number of nodes involved present in this component are 4 and the number of edges are 6, so how many pairs are possible? This if it is complete, there is an edge between every two pairs, every pair. So how many pairs are possible here? That will be formula, like how can we choose 2 from 4? That will be 4c2. That will be like 4 into 3 divided by 2. So there can be 6 pairs possible, and all those 6 pairs have an edge. So there has to be 6 edges, 6 edges in that component or in that connected component or a subgraph. Then we can call it as a complete component. So if we are able to find number of nodes and edges in a component, then we will be we can be able to say whether it is a complete component or not. So next the question is, how will we able to find the number of nodes and edges in a component or in a graph? How we can do that? We can try to do that using DFS. Let's take an example of this. We start with 1 and we know its children are how many? It has 3 children or 3 neighbor, that is like 2, 3 and 4. 2 we have like 3 children, but 1 is already visited, so we will be having 3 and 4. And 3 has, this is the DFS traversal, 3 has 4, right? So what we will do, we will apply DFS on this node. So we will be visiting every node only once uh, with a visited array. So what we will do, we will count the number of edges of every node we visit. So what we will do, when we apply DFS, this returns the number of edges of this 4, that is 3, and 1 the node number of nodes it has, that is 1 comma 3, because 4 has 3 children, so it returned 1 comma 3 here. What does it return? So it will add its node and children, it will return to true. So 3 has 3 children, right? That is 2, 3 and 1. 1, 2 and sorry, 1, 2 and 4. So what it will do? So it will return 2 comma 3, 1 comma 1, 1 plus 1, that is 2, and 3 plus 3, that is 6. Will return 2 plus 6 here. So what does 2 do? 2 will do the same thing. So it will return 3. How many children that 2 has? 2 has 3 children. So it will return 3 comma 9, and 1 will return 4 comma 12. Right. So this is because this 12, this 4 is correct number of nodes. But this 12, what happened is we counted the now nodes 2 times, because we counted this edge when we this edge once when we were counting the number of neighbors of 2, and we again counted this edge when we were counting the number of edges of 1. So this number has 2 times of edges. So what we will do, we will just divide it by 2. So we got 6 as edges and 4 as nodes. Now what we will do, we will just verify whether this is equal to 4c2 or not. If it is equal, that is like 4c2 is 6. If 6 is equal to 6, we will count it as a connected component, otherwise not. So let's check whether this holds good for one more subgraph or not. So what we will do, 1 2 3 4. So we'll just do this thing. So we started with 1. So 1 has 3 children, 2 3 and 4, right? Then we visited to 2 first. 2 has only 2 children, that is 1 and 3. We will not go to 1 because 1 is already visited. We have 3. And 3 has 3 children, but 1 and 2 are visited. So what we will do, we'll go to 4, right? 4 has 2 children, but both are visited, so we won't go. But it will return 4 has 2 children and 1 node. 1 comma 2 is returned here. But 3 will do, 3 has 3 children, and so it will return 2 comma 1 plus 1 is 2, and it will 3 plus 2 is 5. But with 2 return, 2 has 2 children and 1 node. So 3, 5 plus 2 is 7. But 1 has 3 children and 1 node. 4 comma this 4 comma 3. 1 has 3 children, right? So 10, right? 7 plus 3 is 10. So there are actually 4 comma 10 by 2, that is 5 edges. If we count edges here, so 1 2 3 4 5, so there are 5 edges, right? So this method works. So we just need to apply this logic here in code. So let's start writing code here to check whether our solution works or not. So what we will do, we will do this thing. First we will write code for uh, like finding out connected components. There we will apply this difference, this logic, that whether it's a complete or not. So what we will do, we will first make a visited array, because we need a visited array. So we will make a boolean array visited boolean will be of size n. What we will do next, we have to make a graph. Since these are edges, we'll make a graph. What will graph be? We will use array list of integer array. Array list of integer array graph. Array list array of size n. Very simple. Next, what we will do, we will initialize this array for int is equal to 0 and plus we will do drop of I is equal to new array list of integer. Okay, so we got a graph, we got visited array. So we will initialize int answer is equal to 0, and what we will do, we will return that answer. So we just need to loop over every int node is equal to 0, I less than n, I plus plus. What we will do, the connected components logic, we will just check if the node is not visited. Not visited, then only we will explore this. What we will do, we will call if it is a if is complete component, connected component of this subgraph I visited in graph. We will just make answer plus plus. Otherwise we were just doing is connected component, that is like we were traveling just DFS. I will make this function private boolean. Let's copy this, is complete int node, and then we will be having boolean array visited, and then array list of integer array graph. So what we will do, we have to get the this thing. So what we will do, we will call this thing get nodes and edges from this graph. We want this, we will pass it the node, pass it the visited array, and we'll pass it the graph. So it will give us up two values, right? So we will use a pair data structure to get those. So what it will do, it will be an integer of integer, and it will be pair. So the nodes will be equal to p dot get key. So int edges will be equal to p dot get value. Next int expected if edges is equal to this divided by 2, and expected edges will be this, how many nodes into nodes minus 1, the formula of NC2, that will be n into n minus 1 divided by 2. 2 factorial is basically 2. So this is if what we will do, whether it's a complete component or not, expected edges should match the edges, right? Actual edges. Edges is equal to, it's very simple. Now we just have to calculate edges and nodes with the method will be integer of integer get nodes. So this is a hybrid concept. We are using DFS and the mixture and the combination of other concepts to solve this problem. So every problem that we will be solving will have similar kind of problem. That will not be a complete, like very basic problem based on some concept or some algorithm. Usually the problems asked in the interview will have multiple combination of different concepts involved in the problem. So we need to pick up these patterns which will help us solve like a combination or hybrid concept problems. And even every context, in any context on LeetCode or code forces, no problem will become completely based on a pure algorithm or a concept we learn. It will always be always be having multiple concepts involved in. So what we will do, we will mark this node as visited first thing as we do in DFS. Then what we will do, we will calculate, we will initialize r its own value. Int nodes will be 1 because this is a node, and then int edges will be how many graph, all its neighbors, right? Graph of node dot size. Graph of node will be an array list, so size will be this. So we will loop over int neighbor of all its neighbors. So what we will do, if it's already visited, we will just continue, and if it is not visited, what we will do, we will just do nodes plus is equal to this. What we will do, we'll receive a pair, right? So pair p is equal to, call the same function with neighbor with and graph. We will get p. So nodes will add the child nodes of a children, p dot get key. Then comes the edges. Edges is equal to same thing, p dot get value. So we got this. Then we will return new pair of this nodes and edges. Very simple. Let's just try to compile and run whether it runs or not. There are any compilation problems? Yes. So what it is saying that get key, right? So binary operator plus bad operand times her. So it is, so this doesn't explicitly say that it has integer or integer. So let's just try to compile it now. So it's saying it's wrong answer. Output is 6, but this is 3. And it is also saying it is 6, but it is 1. Let's just try to debug whether it's what's wrong here. So we are doing the same thing. Nodes we initialized with 1, graph of node of size, and visited we are marking true. And if it is, if visited, okay, we are continuing, that is fine. Get value, get, it's just doing this thing. This looks fine to me. And then we got number of nodes and number of edges, and we divided it in by 2. Here nodes into node minus 1 divided by 2, returning also correct. So not of visited, then only we are just doing this. Okay, what we didn't do, we didn't initialize the graph. We initialized the graph, but we didn't form the complete graph. We forgot to do this. So this will be int array e over edges. So we get an every edge. We will form a graph. Graph of edge of 0, we will add edge of 1. Graph of edge of 1 will add edge of 0. Now it should work. Okay, it's working for 2 test cases are passing. Let's just try to submit it. Yes, submitted. So this is a solution. So what we did, we just used the connected component logic, and we just verified whether a connected component is complete or not, right? Whether it's a complete or not. How? The simple logic for complete means every pair has an edge. Every pair is basically choosing 2 from number of nodes. Uh, that is like a combination, choosing 2 from total number of nodes. So that is basically the number of nodes present n c2. We know that we know formula to calculate it, and we know calculated or number of edges by DFS, and we just verified whether it's a connected component or not. This is the logic of whether calculating whether a component is a connected complete connected component or not. And this is like variation of DFS, or we just used this concept in DFS to get the number of edges and nodes from this subgraph. The problem is very simple. In next video we will look into next concept, that is basically the number of islands. We will calculate the number of islands in a 2D graph, which will have the same logic, like calculating connected components in a graph. Similarly, we will be applying that concept or logic on a 2D grid or a 2D matrix. Okay, bye bye.